Okay, hello everyone. We are back for another chemistry squad. My name is Nketia, or just NK for short. And today we're going to be going over oxidation and reduction. I know there was a lot of demand just to go over those two topics. So really excited to start the session as well. We're just going to give it just 5 more minutes or so. I know a few people are rolling in at the moment, so um, by all means, if you just want to sit and get comfortable, then well, we'll start at maybe 6:05. Or yeah, 6:05. Now it'll be 4 minutes, but we'll start shortly. As I always say, do make sure to check out some of the other really interesting and exciting content on the My Tutor YouTube channel. If you do like this chemistry squad and other chemistry squads or other study squads like this one, make sure to smash that like button as well. Ultimately, we put all this content together for you guys, and if we don't know what you like, we can't offer you more of that content and more of that resource to support you in your learning and your academic endeavors. So do make sure to smash the like button, give as much feedback as possible. There is a feedback link that does go around. I think it's actually in the description of this video as well. So you can also check that out too. You can just click on that link, pop your feedback in, um, and then yeah, you can give as much feedback as you'd like. Okay, so we'll just give it 5 minutes or so. Well, 3 minutes now actually. We'll start at 6:05, and then we'll get right into looking at oxidation and reduction. Okay, so it is 5 past. I think we should just get started. Now, my question is, have I been organized? and brought my pen. Yes, I have. Fantastic. Okay, so we're going to go over some oxidation and reduction. Now, if you don't get a chance to watch this live, it's not a problem because you can always watch it retrospectively because it's all uploaded onto the My YouTube channel. So that's always useful, isn't it? So reduction and oxidation. And I know someone also wants to go over displacement reactions as well. So what I'll try and do is weave that in there a little bit, since I'm sure the displacement reactions that we're really referring to are those of the halogens, so group 7 of the periodic table. Now, oxidation and reduction are both examples of reactions that you may have come across, you may not have come across, absolutely fine. You can class them in the same way that you would class an addition reaction or not a subtraction reaction, but maybe, addition or I'm thinking addition, subtraction, multiplication, division. No, either like an addition reaction, you may have a decomposition reaction. You can classify oxidation and reduction in a very similar vein. Now, when we think about oxidation and reduction, what we're really thinking about is electrons. Okay, we're thinking about electron movement and transfer. Now, hopefully, this is a concept that you're not too unfamiliar with, because electron transfer is something you would have seen in the context of um, metals and nonmetals when they react. You may have seen them in the context of nonmetals when they share electrons. So generally, the idea of electrons moving around and not being in a fixed place hopefully isn't an entirely new concept to you. But what we're really thinking about when it comes to reduction and oxidation is we're thinking about the loss and the gain of electrons respectively. And a really, really fun and easy way to remember which is which is using the mnemonic oil rig. So oil rig stands for oxidation is loss and reduction is gain. And that pertains rather to the direction of electron transfer when we're thinking about oxidation and reduction respectively. So when we think a little bit about oxidation, what we're saying is that oxidation is the loss of electrons. Similarly, reduction is the gain of electrons. So when something loses electrons, it's being oxidized. And when something is gaining electrons, it's being reduced, which is really, really useful for us to understand. Now, when you're going over this topic, what you'll probably find is you're introduced to something called the reactivity series, where you have this list of different substances, different elements, and they're all on a list where everything at the top is more reactive, everything at the bottom is less reactive. And you could think about displacement reactions in that context too. There's a lot of content to cover there that I don't think we'll get time to go over today, but that's not a problem because it's quite easy to go over once you sort of understood the basics, which hopefully we're going to cover in today's session. So far we've talked about how oxidation is defined as the loss of electrons and reduction is defined as the gain of electrons. So we've understood that, and we've understood it's all to do with electron transfer. Again, if you don't get a chance to watch this live, that's not a problem because you can always watch it back on the My Tutor YouTube channel, so that's not a problem at all. So we've thought a little bit then about what oxidation and reduction are. I think one of the most common things that you need to be able to do is you need to be able to write out what I'll refer to as half equations. And half equations are a way of you showing what's being oxidized and what's being reduced. So here's an example. Let's take, what's a good example of an oxidation and reduction reaction that's quite straightforward? Mm, let's say, okay, here's an example. So copper sulfate plus iron goes to form iron sulfate and copper. Now, a lot of the time with these reactions, what you'll need to do is figure out what's being oxidized and what's being reduced. Now, me writing out that equation as it is, I don't think that's particularly clear. of what's being oxidized and what's being reduced. Actually, that's a little bit challenging to figure out based on that on its own. But the great thing is we can break this equation down, this balanced equation, into something called an ionic equation. And an ionic equation, it helps break all the ionic compounds down into their constituent ions, okay, their respective ions. What we then do is we eliminate what we refer to as the spectator ions. And a spectator is just something that watches, or someone that watches, doesn't really get involved. And with ions in chemistry, a spectator ion is one that doesn't really get involved in the reaction. It doesn't really change. So how it looks on the left-hand side is exactly how it looks on the right-hand side. Okay, so not really much going on there in that respect. So we can do that here. We can break up copper sulfate into individual ions, and we can break up iron sulfate into its individual ions. Now, we can't do that with the iron on its own and the copper on its own because they're just elements, okay? They're just atoms, so there are no ions to break it up into. But we can apply the same thing with the copper sulfate and the iron sulfate, respectively. So let's do that now. And I'm going to do this in a slightly different color, just so we can see the difference. So we'll do it in strawberry. Yeah, okay. So copper sulfate consists of copper 2 plus ions and sulfate ions, which is SO4 2 minus, plus iron, which is just going to stay the same. Nothing going on there. It's just an atom at this point. Goes to iron 2 plus and sulfate ions and copper. Now this has made things a lot easier because now we can see which ions there are. We can see what's changed and we can see what hasn't changed. Now the great thing is that the copper has clearly changed. It's gone from having a charge of 2 plus to having no charge. So that tells you actually that this copper must have gained electrons. We've said that reduction is the gain of electrons. So if you have a positive charge and then all of a sudden you have no positive charge, you become neutral, that must mean that you've gained a negative charge because remember, we're just focusing on electron transfer. It's not as if you can gain or lose positive charge. You just gain or lose negative charge, and then it becomes a bit of a balancing act. So if you have something that's positively charged and you add negative charge, it just becomes neutral. Similarly, if you had something that was positively charged and you took away negative charge, then that would just mean that it's become more positive. So it's all relative based on how many electrons you have, how much negative charge you have in comparison to how much positive charge you have. Now, that can be a little bit tricky to get your head around, but if you just remember in chemistry that you're looking at electrons, you're focusing on electron movement, then it makes things a lot easier. Okay? Just focus on the electrons and ask yourself, am I gaining electrons or am I losing electrons? Am I becoming more negative or am I becoming less negative? If you think about it from that perspective, it gets a little bit easier. So, we've written out this ionic equation, right? We've split everything up into its constituent ions. And now what we can do is we can break up what are referred to as the spectator ions. And the spectator ions here is clearly the sulfate, because SO4 2 minus is the same on both sides. That's not really changed. So actually, the key reaction is copper 2 plus iron gives you iron 2 plus and copper. Now that looks quite odd, doesn't it? Because it almost looks as though the copper 2 plus has gained electrons and the iron has lost electrons. And that's exactly what's going on. So, in essence, we can say that copper is being reduced and iron is being oxidized. And now what we can do is we can show that by drawing what's called a half equation or writing a half equation. And a half equation is where we split apart the oxidation and the reduction sides of the reaction, and then we balance them out using electrons or hydrogen or water. So in this instance, what I'm going to do is I'm going to write out the equation for each, and then I'm going to go about balancing them. Oh, hi, Mohammed. How are you? Hi, Mikhail. How are you? Good to see you as well. Great to see both of you today. So, when we think a little bit about writing out half equations, I think the key thing is to have a process, one that you always follow. So, the first thing that I would always do is I'd write my reactants and then write my products. So that's what I've done for both of my half equations here, right? I've written out the reactant, so I copper 2 plus and Fe, and I've written the product, so Cu and Fe2 plus. The first thing I always think to myself is, do I have any oxygen? Now, generally with half equations, if you want to balance out oxygen, you add water. Now, there's no oxygen here because we've eliminated the sulfate, so we don't need to add any water to balance out oxygen, so that's fine. So we can move on to our next point. I can balance out hydrogen by adding H plus ions or protons or H plus ions, however you want to refer to them. Now, in this instance, I have no hydrogen to balance out, so don't need to add any hydrogen either. So this is actually quite straightforward. This isn't too bad so far. And the last thing that I need to do is I need to balance out the charges, and I can only do that by adding electrons. Now, this is the part that whenever I've marked past papers or I've had lessons with students, it always gets a little bit complicated. And so it's really, really important that you remember something. Charge has magnitude, but in this context, it also has a direction in the sense that it could be positive or negative. So it's really, really important that you remember that because it does affect your balancing. So Mohammed has a question. Is copper oxide black or blue? Okay, so copper oxide, I think the blue you might be thinking about copper sulfate. So copper oxide itself is like a black compound. Okay. Now, when you then take that copper oxide and you mix it with, let's say, sulfuric acid, which might be the direction you're going in with this question, you then end up with a bit of a blue solution. And the reason you have a blue solution is because you end up with copper sulfate, but copper 2 plus specifically in water, those ions are blue. Okay, so copper oxide itself is black. Okay, it's a black powder or a black cube, depending on what form it's in, whether it's powdered or just a block. But it ends up forming a blue solution because in water, when it's dissolved, the copper 2 plus ions give a nice blue color. So that's why. Okay, so it looks black. But when you put it in solution, when you react it with something, it'll appear blue because the copper ions um, they dissolve in water to give you a nice blue solution. Okay. Hopefully that makes sense. Can be a little bit confusing, but that's the reason, that's the rationale. Okay, excellent. So we've talked a little bit about this. Okay. Do I have any slides? So we don't have slides for the live streams. Um, do I have slides that you can use? Um, Generally, when it comes to revision, I would definitely say if you already have notes from school that you can utilize, then by all means do so. I think the CGP guides are pretty good. But no, we don't quite have slides that we'd upload or anything like that, since it's all live streamed. But you can always watch this back on YouTube afterwards anyway, which is essentially similar to slides. It's just you can't download it or anything like that. Um, but balancing. So when we think a little bit about balancing, what we can do is we can just add electrons. And we have to be very, very careful when we're balancing charge because a lot of the time we'll add electrons to the wrong side, and that means that we don't balance it correctly. And I'll show you an example. So copper 2 plus, that's two lots of charge. Now instinctively you'd think, well, if I've got two lots of charge on the left-hand side, I should add two lots of charge on the right-hand side. So I'm going to add two electrons to the right-hand side. But that wouldn't be correct because then I'd have two plus on one side and two minus on the other side. And that's not the same because one is positive and one is negative. What I should be trying to do is making sure that the charge is same overall on both sides. So if I've got copper 2 plus here, which is 2 lots of charge, I should add 2 electrons to the left-hand side, because 2 lots of positive charge would cancel out 2 lots of negative charge. So overall, I've got a charge of 0 on the left-hand side, and I've also got a charge of 0 on the right-hand side. So now that's balanced. And I can do the same thing with iron. So iron's got a charge of 2 plus on the right-hand side and nothing on the left-hand side. So what I can do is I can add 2 electrons to the right-hand side. And now the charge on both sides is 0. And that's essentially how I've achieved balancing. Okay. Um, so from that perspective, I've now ended up balancing these half equations. Okay, so I've got 2 electrons on the left-hand side and 2 electrons on the right-hand side. And actually, if you think about what's going on here, this makes sense because adding 2 electrons to copper 2 plus is reduction. And we said that copper is being reduced because copper is gaining electrons, and my half equation shows me that. Similarly, we said that iron was being oxidized, and that shows me that because iron is losing electrons to form iron 2 plus ions. Okay, so that is reduction and oxidation. Okay, so Mohammed has asked, why can we add 2Na, like Na2SO4, but the rule is you can't add a 2 in front of an element? Okay, I think I've understood your question. Let me erase I'll erase the top bit. So I don't want to erase all of it because we haven't quite finished going over all the content for today's session. So, I think what you're probably asking is why is it that for something like sodium sulfate, which is what you've used as an example, I could put Na2SO4, but then I can't, let's say, for instance, if I wanted to balance out, um, I don't know, let's say, I'm trying to think of a good example here. Um, a good example is like H2O. I can't just put a 2 there. Okay. Or I can't put like a 2 there or something like that, right? That might be your question. So the difference is that in the case of the first substance, sodium sulfate has this formula. And the reason sodium sulfate has this formula is because each sodium ion, since we've established that sodium sulfate is ionic, each sodium ion has a charge of +1. Each sulfate ion has a charge of 2 minus. So then if I were to then form a compound, a formula from that, I need 2 sodium ions for every 1 sulfate ion, which is why it's Na2SO4. Okay. Another way of figuring that out is something called the crossing over method, where you'd write your 2 ions out and you'd draw arrows crossing over, and then you'd put the magnitude under each one. So then Na2SO4. Okay. But if you had a compound, a formula already, let's say H2O for instance, and you need to try and balance out the oxygen, you can't just add a 2 to the O in H2O because then it's no longer water, okay? H2O2 is a completely different substance, so that would be something called hydrogen peroxide, for instance, which you definitely can't drink like water, okay? So that's the difference, okay? One situation is when you're constructing a formula for a compound, like sodium sulfate, Na2SO4. The other is if you're trying to balance an equation. So if you're trying to balance an equation, all you can do is add large numbers in front of the whole substance, so a coefficient, if you will. So if I wanted to balance out water, I'd have to put like a 2 there or a 3 there or something to that effect. Okay, you're not allowed to just add a 2 to the oxygen because then it's a different substance altogether. Then that's H2O2. Okay, so that's what I would say in that respect. Okay, hopefully that's answered your question. If it's not, then by all means let me know and we'll see what else we can try and figure out. Okay. Um, cool. Okay. So the only other thing that I want to mention, just because I noticed that we're getting towards the end of the active teaching part, and then we're going to go into a bit of a nice little Q&A for 15 minutes or so. is just to talk a little bit about displacement because we didn't quite get to talk about that too much. Now, displacement can be defined as um, where a more reactive substance essentially replaces a less reactive substance. Now, like I mentioned at the beginning of the session, you can refer to the reactivity series, which details every element that you'll need to know and where they rank in terms of how reactive they are relative to one another. So generally, you'll have things like potassium and sodium towards the very top, and you'll have things like gold and platinum right towards the very bottom, so they're not particularly reactive at all. And the idea is that a more reactive element can displace or essentially replace a less reactive element. So that's kind of the that's sort of the thought process there, okay, in terms of displacement. Now, I did mention that I was going to use the halogens as an example. Okay, because it is something that comes up every so often, and I suppose you can sort of think about it in terms of oxidation and reduction in that respect, which is what we're talking about today. So what I'm going to do is I'm just going to erase some of this. I think I'll erase this part because I don't really want to get rid of the half equations because I think that was quite good. But again, you can always rewatch this afterwards, so not a problem at all, even if I am erasing it now. So, if we think a little bit about our halogens, we know that they consist of fluorine, chlorine, bromine, and iodine. Okay, so we've got these different substances, okay, all these different halogens. And we know that fluorine's towards the top, and we know that iodine is then at the bottom. Okay, so we've got our different halogens there. And generally, what we can say is that the more reactive halogens can displace the less reactive halogens. So chlorine, for instance, if I was to bubble that into a substance that had, let's say, potassium bromide in it, um, that can displace the bromide ions to form potassium chloride and bromine. Okay, and I know this because bromine is lower down uh, group 7, so it's less reactive. And I would balance that out like so. Similarly, if I want to take bromine and then use it to displace um, potassium iodide, then I'd end up with potassium bromide and iodine, like so. Okay. Unfortunately, though, if I wanted to try and take bromine and use it to displace potassium chloride, that doesn't work because chlorine is more reactive than your bromine. Okay, so it can't displace it. So now you have a question. How would I practice chemistry? That's a very good question. I think I'm going to come back to that question in the Q&A session though, because I think you could. There are many ways in which I would give advice on that. Um, so I'm going to come back to that question. It's a very good question, something I can sort of touch on a bit later on. So I'm going to come back to that. Um, so. And then you said, is bromide, Mikhail, you've asked, is bromide more reactive than fluorine? No, so fluorine is more reactive than bromine. So I'm gonna sort of touch on that now. So in essence, because chlorine is more reactive than bromine, the chlorine can displace the bromine or the bromide ion from potassium bromide. Similarly, because bromine is more reactive than iodide, it can displace the bromide or the iodine from the potassium iodide. So the general rule of thumb is that your reactivity goes down as you descend group 7. It's not the same as group 1 because you have the opposite in group 1. In group 1, reactivity goes up as you go down the group. So be careful with that one. Okay. Um, can you use a clearer website because it's slightly blurry when I write the chemical equation? I'm not actually using a website. It's just like, well, not quite Microsoft Paint. It's just the system that we use to stream. So I don't know. Maybe try. I don't know whether it might be the resolution on your phone. Um, although my graphics tablet isn't the best either. Um, but I can see what I could potentially do for next week anyway. Um, it's just to make sure all the content is on the screen at the same time. But what I was saying was in terms of your halogens, they become more reactive as you go up the group. So fluorine is more reactive than chlorine, chlorine is more reactive than bromine, bromine is more reactive than iodine. So the more reactive halogens can displace the less reactive halogens. Okay. And this is displacement. And generally, we can apply the same thing when we're thinking a little bit about your reactivity series. So the more reactive metals can displace the less reactive metals as you go down the reactivity series. Okay, and I think that's it in terms of actual teaching. What I'm going to do now is just move on to a quick Q&A session. Okay, so you've got 15 minutes or so where you can ask me any questions at all. There are already a couple of questions that have already been asked that I want to touch on, mainly how to practice chemistry, and then I'm going to open the floor to any other questions. But thank you for joining. I'm sure before you do leave, make sure to fill in the feedback form that hopefully will be popped in the live chat. Um, so do make sure to fill that in. It just means that anything we can do to improve the sessions, you can let us know, and then we can then improve them at my tutor. Ultimately, these sessions are for you, and so without you, there are no sessions, and we want to know what helps you and what supports you in your academic endeavors. On that note, I'm going to answer Mohammed's initial question, which I said I was going to come back to later, which is now, which is how do I practice chemistry, or how would I practice chemistry? It's a very good question, and I think it depends on what your strengths and your weaknesses are. I think the first thing to consider is what do you find difficult about chemistry? Is it the content? Is it the questions? Or is it a bit of both? I'm always of the firm believer that past paper questions and writing notes and reviewing content throughout the year is a very good approach to learning the sciences. Okay, I'm not keen on cramming towards the end of the year because I think you just end up getting stressed. You try to remember everything. It doesn't work, in my opinion anyway. It might work for some, but I'm not a huge advocate of it. I would much rather you take your time throughout the year to really truly understand the content. Um, so I would make notes. There are many websites out there where you can access past papers and past paper questions, depending on your exam board. So either AQA, Excel, or OCR. You can, or WJEC, sorry, or even the Cambridge spec, that's five. Um, you can just go online onto their actual website and you can access past papers from each year series. Maybe not the more recent ones because there's a locked way to teachers, but you can certainly access a good few series of past papers that you can practice. Additionally, you can also access examiners' reports, which is actually quite useful, and they can give you a bit of insider intel as to how the examiner thought when they were marking certain questions and what their feedback is. And I think that's really, really useful. I think that's a really, really good resource. There are other websites like Physics and Maths Tutor, all one word, Save My Exams, again, all one word, where they can group together certain topics into certain question packs, so you can practice those as well. I think the key is when it comes to practicing chemistry is firstly, it's repetition. So don't expect to understand it the first time you've gone over it because I think that's a fairly unfair expectation to have. Be willing to go over things multiple times. And going over things multiple times doesn't mean you're not good at chemistry. It just means you're being thorough, which ideally you'd want to be because that helps build your confidence over time. Um, Also, don't be afraid to ask for help. I think this goes for all the sciences, chemistry in particular, because I know chemistry can be quite challenging for many. If you've identified that you don't get something, okay, don't sit on it for too long. Okay, try and go over it again on a different day. And if you still don't get it, ask a friend who might understand it, ask a teacher, or you can even ask someone at my tutor because we're all here and we're ready to help. Um, the key thing is if there are things you know you don't understand, don't wait, try and address it sooner rather than later. Because what happens is, um, if you leave it for too long, then there are many things that then you don't get, and then they all pile up, and then it just becomes stressful unnecessarily. Um, so I would definitely say, don't be afraid to ask for help. Ask for help sooner rather than later. Um, but yeah, to practice chemistry, make notes, review your notes over a long period of time. You know, don't wait until you're told you have an end of topic test, or don't wait until like 2 weeks for the exam. Just get into the habit, get into the mindset of just revising chemistry regularly. Okay. I hope that answers your question. And we actually have a follow-up question, which is, what do I think the hardest science might be? So this is a very subjective question. I honestly, I think I found physics the hardest personally. Um, so I'm a pharmacist, and ironically enough, as I say, I don't really like maths that much. It's not that I don't like maths, but I prefer maths when it's applied. So um, for pharmacy, it's fine because I'm applying the maths to a real life situation, like a drug or a dose or something like that. Um, but then in physics, when I was sort of looking at anything outside, like basically anything outside of mechanics was fine. But then anything in mechanics I found challenging because I didn't feel like it was applied enough for it to click for me. Everyone has their own difficulty when it comes to different sciences. I know some people find biology difficult because there are all these technical words that you have to try and remember and use that sound similar. And for some people, it's chemistry for many a reason because chemistry is renowned for being this really challenging science. I think everyone has their own difficulty with the sciences. Some people find all three sciences easy, some people find all three sciences difficult. I think the important thing that we should try and do as students is try and identify what it is that we find difficult about the science. Because if you pinpoint that, you never know. You might find that whatever it is you find difficult is applicable to another science. So if it's maths that you find difficult, like the math component of the sciences, then that could be why you find all three sciences challenging because there's a maths component in all three of them. So biology, chemistry, and physics. Um, if it's the key words that you find challenging, then maybe you find physics less challenging. I'm not saying that there aren't keywords in physics, but it could be that you find biology more challenging because there are more keywords to remember, or you feel like there are. So there are lots of different things to try and consider. I think the key is just to try and isolate what you think the difficulty is. And again, you can always ask your teacher for feedback. I think we're too afraid to do that. There are many teachers would be more than happy to sort of give you one-on-one feedback if it means that you can then improve how you're doing, because that's really the aim, isn't it? And again, you have teachers. We're here at My Tutor as well. We can always try and give it advice and try and support wherever we can. So that's the other thing that I would say. That's also a very, very good question. Okay, thank you for asking that. Very good question. So, does anyone have any ideas as to what we might want to cover next week, next Thursday? I was thinking rates of reaction, but then I'm really biased when it comes to chemistry. I think kinetics is one of my favorite areas of chemistry. Um, but we've done really well so far. We've gone over bonding, like structure and bonding. We've gone over atomic history. We've gone over, well, we've just gone over reduction and oxidation. I think we've gone over something else as well. But I can't remember what it was. It's been a long day, as you can probably tell. But electrolysis. Okay. Yeah, we can certainly go over electrolysis. That is doable. We can certainly do that, which actually might be quite nice because that's a nice little follow-on from oxidation and reduction, which is what we went over today. So yeah, we can certainly go over electrolysis. That's a good suggestion. Thank you, Mohammed. Very good suggestion. Okay, because we're getting towards the end of the session, what I am going to say is firstly, thank you all for joining. Um, oh, no, actually, before I close, there's another question. Um, I wrote that the modern periodic table has electrons and electron shells. Would that be 2 marks? Okay, so I think this depends on the question. If the question was about like the modern periodic table itself, I think I think that's probably a comparative question. So the modern periodic table, some of the features are that it is arranged in atomic number rather than atomic mass. The other thing as well is that it's arranged in groups which are, they're grouped based on their properties as well. Um, so that's another point to make. Um, you could say that it consists of like a section of transition metals. If you were asked about the structure of the atom, yes, you could say that the modern nuclear model consists of electrons as well, and the Bohr model then elaborates on that and then talks about electron shells. But I think if they're asking you about the modern periodic table, they would want you to talk about the arrangement of how all the elements are arranged. So making reference to how they're arranged in order of atomic number. Okay, so that's what I would say. But I'm not too sure of what the question is exactly. So, but based on that, that's probably what I would have said or why I would have gone along those lines. Okay, so we're going to go over electrolysis next week, which is exciting. Okay. Um, as I always say, make sure to smash the like button of this video if you did find it useful, if you did find it enjoyable. Okay. Um, and do make sure to fill out the feedback form, which hopefully will be popped in the live chat in today's session. If not, no worries, because there is a link in the description of this video as well. Okay. In the same link of that video, you can also send that to friends if you have any school friends who you think might find these chemistry sessions useful or the coding sessions useful. I know there's also a math squad as well. Um, the math squad that you could also check out as well. So do make sure to check that out too. Um, But otherwise, I hope you all have a lovely evening. Do make sure you stay safe. The weather's getting it's a bit touch and go actually. It rained for me today quite heavily at the beginning of the day. I think it's lightened up now. Um, but otherwise, I hope you're staying well, staying safe, and studying hard. The summer is coming up though, so hopefully you all have some plans for the summer. Um, and otherwise, I'll see you all next Thursday at 6 o'clock. Again, make sure that you know that the squads are always at 6 p.m. on a Thursday from now until the end of July. Next week will actually be our fifth squad, so I think we're going to be halfway. Um, but otherwise, yeah, enjoy your evening, and I'll see you all next week. But take care until then.